universe isn't giving up its secrets so easily. In 1998, I joined the board of editors at Scientific American, where I oversaw the publication of articles written by some of the world's foremost researchers. That same year, astronomers redrew our picture of the cosmos by discovering that supernovas in distant galaxies were farther away than they'd expected. Their theories had predicted that the expansion of the universe should have slowed down over its 14 billion year history, due to the combined gravity of all its matter. But the supernova results showed just the opposite. The cosmic expansion is actually accelerating. In an attempt to explain the findings, theorists proposed that an entity called dark energy pervades the universe with a repulsive force that works against gravity. But they could only guess what dark energy is. An inherent property of empty space? A type of dynamic field that's remodeling the universe? And over the past 2 decades, they haven't come much closer to figuring it out. There's been a similar lack of progress in identifying the nature of dark matter, the unknown substance whose gravity seems to hold galaxies and galactic clusters together. The physicists' ignorance is especially embarrassing because dark energy seems to constitute 68% of the universe's energy content, and dark matter comprises another 27%. The total amount of ordinary matter, all the stars, planets, gas clouds, and so on, accounts for only 5%. In other words, we understand just a tiny sliver of the cosmos. Researchers have tried to find answers using the tools of particle physics, but those efforts have fallen short. The standard model of particle physics, which is a type of quantum field theory, describes all the known elementary particles and explains 3 of the 4 known fundamental forces: electromagnetism and the strong and weak nuclear forces. But it can't explain gravity. Quantum theory, which does an excellent job of describing how particles and forces interact at the atomic and subatomic scales, is mathematically incompatible with general relativity, which explains large-scale phenomena such as galaxies and gravity. Starting in the 1970s, physicists attempted to merge these 2 disciplines by developing a theory of quantum gravity that would describe the gravitational force at the smallest scales and highest energies. The most prominent effort involved reimagining the elementary particles as vibrating strings. Dubbed string theory, this project advanced rapidly in the 1980s. The big advantage of string theory is its potential ability to describe all particles and forces as different manifestations of a fundamental one-dimensional object, a string that is infinitely slender and only 10 to the negative 35th meter long. That is about a trillionth of a trillionth of a trillionth of a meter. A closed string, that is a minuscule loop, would have the properties of a graviton, the hypothesized carrier of the gravitational force. An open string, with 2 endpoints, could describe any of the other particles, depending on its mode of vibration. A string vibrating in one type of pattern would be an electron, for example, and strings vibrating in other patterns would be quarks, photons, neutrinos, and so on. String theory, though, has big disadvantages too. To generate all those particles and forces, the infinitesimal strings must vibrate in 9 spatial dimensions, 6 more than the number we've observed in our 3+1 dimensional universe. String theorists deal with this discrepancy by postulating that the extra dimensions are curled up into manifolds too microscopic to be observed, like the tiny curls of fabric in a seemingly flat carpet. But when physicists tried to derive equations and predictions using this approach, it proved to be hideously complex. Instead of discovering a unique theory of everything, they developed 5 intriguing but incomplete theories. In each theory, moreover, there's a huge number of ways to fold up the extra dimensions. And because the shape of